is called the Riemann sums. This is not a hard topic at all. We're not using integrals or not hard integrals for this one. But the thing is that it's a little tedious in a way. You need to do a lot of calculations. Okay. Now, you remember I already explained since Monday that basically when you have a definite integral helps you to find the area under a curve, under a function. For example, this one is when you have a function f and you have the unit from a to b and we want to find the area. We know that it's a definite integral, right? But before the integrals were developed, to find the area in the lower curve, they used different procedures. Okay? One of those procedures was using known figures. What do you mean by known figures? Well, for example, when you have a rectangle, that's an easy formula, or a square, or a triangle, or a circle, right? But when you have something like this, a figure that is limited by a function that is not regular, like a line or something like that, like a curve in this case, it was easier to know to use figures such as rectangles, trapezoids, or triangles, or whatever, to estimate the area. In what way? For example, in this one, trapezoids or whatever, if I want to use rectangles to estimate the area, I can do that. By doing what? Well, by dividing this area in rectangles. Such as these ones, let's say this, like this, like this. If you observe, I divide the whole area in rectangles. So, since you already know how to calculate the area for rectangle with base and height, you could estimate the area below the curve. Of course, it's not exact because there's little spaces that are not going to be included in the rectangle. For that, we can use other figures like trapezoids. But the idea is that by knowing the area of these rectangles, we can approximate. And usually, in this case, when you add all of them, it's going to be called a sum. And for that, we're going to use this, which is called the Riemann sums. The Riemann sums is going to be basically that, adding the areas of these known figures to approximate the area on their curve. Okay? Imagine this. I'll give you a real example to understand a little better. Let's say that I have a function that I already know, which is x squared. Imagine that I want to calculate the area, let's say from 1 to 4. 9. Okay? I want to calculate the area from 0 to 4. Okay? I can divide it in rectangles. For example, if I use 2 rectangles, then it's going to be an estimation, right? It's not going to be exact, yeah, but it's going to be an estimation. If I were to use, let's say, 5 rectangles, and you have that, for example, 1, 2, 3, 4, and one more that is going to be here, it's going to be a little more exact. Or, for example, if I were to use, like, let's say, 12, you have something like this. It's a little more exact, even though there's still an estimation, it's a little more exact. So the whole idea is this, for the Riemann sum, we're going to estimate the area by using these rectangles. But by doing what? Simple. In this case, what will be the area of a rectangle? What's the area of a rectangle? For a rectangle, the area is base times height. But in this case, in this situation, what is my base and what is my height? Well, this base here is going to be called delta x, delta x, delta x, delta x. Why delta x? It's a difference in the x value. Or also another one, delta x. This is going to be the base. Now the problem lies in the height. Because to find the height, we have different subtypes of the Riemann sum. Also categories of sub-methods. One of the methods is by using the lower area or the left endpoints. What do you mean by left endpoints? That the left point of the rectangle is the one that touches the graph. If I were to use the right endpoints, which in this case is called upper, I'm using this one, the right parts. If I'm using, for example, the midpoints, then I'm using the middle part of the rectangles. Okay? Do you get the idea? Okay. Let's, yeah.
¿Con qué fin usas uno u otro?
To approximate the area.
Pero tú no le tienes que restar o le tienes que. O sea, tú te da igual de exacto, ¿no? Uno u otro.
No necessarily. Not necessarily. But we'll see by an example.
So you will get the same result by using the different.
No, but for example, let's say if I were to use the left, you have an area that is below the real one or less than the real one. When you get the right endpoints, if you observe, you have an area that is going to be bigger than the real one. So the real area is going to be between those two. And the midpoint in this case will be a better approximation because a little more exact. Because basically this part and this part, they cancel each other in a way.
So an average of the three is the most.
No, we won't do the average. Just want to estimate the different areas. Okay, let's do an example to see what I mean. Let's start with that. So for the Riemann sums, we have three different methods. The right endpoints, the left endpoints, and the midpoints. Okay? Those will be three methods for the Riemann sums. To do what? To estimate area under a curve. Let's do an example by using these figures so it will be easier to understand. Let's start with, let's say that I want to calculate the area below the function y equal to x squared between 0 and 4. Okay? This is my question. Calculate the area below the function y equals to x squared between x belongs to 0 to 4. That is, from 0 to 4, I want to calculate the area using the Riemann sums. But something that is also important to understand from this is that we need to know how many rectangles I'm going to use. Okay, because I can use just 1 or 2 or 5 or 10 or 20 or a million. Okay, but that is going to be also given in the exercise. In this particular example, I'm going to use 5 subintervals.
Eso siempre nos lo va a decir.
Yeah.
¿Y si no vas a rectángulo?
No, that's another one. The trapezoids. But right now, just a straight. But yeah, also trapezoids. Okay, so using 5 subintervals, I want to calculate the area between 0 and 4. Okay? So first, I'm going to start with the left endpoints, the easiest one. Left endpoints. Area, left endpoints. Okay. Tell me, observe the figure. Here's the figure. Already done. How can I get the whole area? What do I do? Ideas? Okay, let me rephrase the question. How do I get the area of the 5 rectangles that I have? Perfect. So the question is, how do I get the area of each rectangle?
You divide the base in 5 and for the height.
Exactly. In this case, for example, I need the delta x because that's going to be the base of each rectangle. How do I get that? Simple. Delta x in this case is going to be what? The highest value, which is 4, minus the lowest value, which is 0, divided by what?
5.
5, which is the number of intervals. So in this case, it's going to be 4 over 5 equal to what? Yeah, decimals, that's fine. Point what? 0.8. Very good. So 0.8 is going to be the base of each rectangle. 0.8, 0.8, 0.8, 0.8, 0.8. So for example, if I want to calculate the first rectangle, is going to be 0.8, which is the base of the first rectangle. Times what? Times the height of the rectangle. But the thing is, how do I get the height of each rectangle? In this case, for example, the rectangle here is not there, but it's there actually. How do I get that? That's what the left endpoint is important for. Because it means that every left point of each rectangle is the one that touches the graph. The left part. The question is, how do I get this value? Because this value represents what? The height of each rectangle. Exactly. I need to evaluate what in the function? Exactly. If this is my first rectangle, this is my lower limit, and this is my upper limit, how do I get the first value? Evaluating what? 0. So it will be what? F of 0. How do I get the second value? F of 0 plus what? Plus delta x. That is 0.8. How do I get this one?
We add delta x.
1.6. How do I get this one? 2.4. How do I get that one? 3.2. So, in this case, for example, to find the area of everything will be 0.8 times what? F of 0. Since the function is what? X squared will be 0 to the square plus 0.8 times what? 0.8 to the square plus 0.8 times 1.6 to the square. 0.8 times what?
2.4 to the square
plus 0.8 times what?
3.2 to the square.
To the square. Do you understand why is the square?
The function.
Because the function is x squared. You're not substituting what? You're substituting each individual value that you get to the square because that's the function. If the function was x to the cube, it would be cube, 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 cube. If the function was sine of x, it would be sine of 0, sine of 0.8, sine of 1.6, etc. Because it's the base of each rectangle. Remember, what I'm looking for is the area of each rectangle and then add all of them. So, it's the base of the rectangle times the height of the rectangle. The base of the rectangle, height of the rectangle. Base of the rectangle times height of the rectangle, and so on. Yeah? Do you understand that? So, in this case, even if you observe, you can factorize. You can even simplify the process because the point is the same for everything. So it's going to be simplified 0.8 times what? 0 to the square, 0.8 to the square, 1.6 to the square, 2.4 to the square, 3.2 to the square. And then do that. Help me with that, please. How much is that? How much is it? Yeah. 15.36. U. Why U? It means units. Units of what? Units of area. Okay? Is that the real area? No. It's an estimation for the area. It's an estimation for the area using the left endpoints in the Riemann sums. Yeah.
¿Por qué las áreas no te dio? O sea, ¿por qué no llegamos hasta la altura de 4?
Because of this. Left endpoints. Yeah, because since I'm choosing the left endpoint of the rectangle, then the last rectangle doesn't get to the 4. just to the 3.2. But even then, you have an extra part that is not considered.
Es la
That's
base.
for the estimation. For the estimation. Do you understand that? Yeah. The height? By evaluating the value. This is 0. This is 0. This is 0.8. So the next one is 0.8. This one is 0.8. This one is 1.6. This one is 2.4. This one is 3.2. This one is 4. So to get the height of this rectangle, you need to evaluate this value in my function. Okay? Yes?
Yes.
Okay, that's for the left endpoints. What happens if the question is, okay, now use the right endpoints. See the figure. To the left, and using the right one. What happens here? The height, is it going to be the same? No. Not this time. Because this time, for example, since I'm using the right endpoints, it means that the right point of the rectangle is the one that touches the graph. So now I want to find this height, this one, and that one. This is the height of this rectangle. This is the height of this one, and this one, and that. How do I get, for example, this height? Would be f of what? 4. Because it's 4, f of 4 is this one. How do I get this one? F of 3.2. F of 2.4. F of 1.6. F of 0.8. Do I need f of 0? No. Because this one covers the height of the last rectangle. Yeah. The what? This one. The endpoints of the rectangles. That's what I want to use. So if you're using the right endpoints, these are the ones I'm going to use. This is the example. I'm going to generalize a formula later, but right now. Right endpoints, the right points of the rectangles are the ones that touch the graph. Left endpoints, the left points of the rectangle are the ones that touch the graph. So in this one, for the right endpoint will be again 0.8. To simplify the process, it's going to be what? 4 to the square plus 3.2 to the square plus 2.4 to the square, 1.6 to the square plus 0.8 to the square. Okay? Should be what? Units. Okay. Is this better than that one? No, just a limit. It means that the real area is going to be between this one and that one.
No.
Not yet. Do you understand that? Okay. Now the next one is the midpoints. For the midpoints, check this. Now the height is going to be different because the midpoint of the rectangles are the ones that are going to be the height of this rectangle. So now it's going to be this one, this one, this one, this one, and that one. So they're different. For example, the very first one, the midpoint of the first rectangle is going to be what? F of what? 0.4. Why 0.4? Because since the base here is 0.8, the midpoint is out of that. The next point is going to be what? How much? 0.8? No. 1.2. Why? Because this one is 0.4, yeah, f of 0.4. The next x value is the 0.4 plus the base, which is 0.8, so it's 1.2. The next one is f of what? 2. The next one is f of what?
2.8.
2.8. The next one is going to be what?
2.6.
3.6. Okay? So, same situation. 0.8, times 0.4 to the square plus 1.2 to the square, 2 to the square, 2.8 to the square, 3.6 to the square. How much is that? Should be 21.2, not 12. Yeah.
¿Por qué con el right conversión de 4? Más en 2.
No. When I say the right one, it's better to use the one that you already have. Since you observe in this case the last rectangle, the point, the right end point here, the one that touches the graph, and it starts where? At 4. So I fall 4. So you go backwards instead. At the right end point, you go backwards. From the last one, start getting backwards to get up. Because that's the right end point, the one that touches the graph. For the left end points, the one that you start is the first one, the first value. This is the left. And the midpoint, well, the midpoint of each rectangle. Okay? Now, which one is better? Well, the last one is more exact. And it should be between those two. It's not an average. It's not an average. But it's between those two, approximately. And it's a better approximation than the other two. Do you get that? Yeah.
You put the right endpoint and the left endpoint as units in an integral, you get the polar.
No, I like that. Okay, fine. Another question about that? How do I get the real? How do I get the real area? How can I prove that this one is correct or between those two? To find the real area, I need to use the integral. Okay, since you already know how to integrate, well, it's easier. So in this case, to find the real area, we integrate. So the integral of what? You already have a and b, 0 and 4. So from 0 to 4 of the formula, the function which is x squared dx. Can you integrate this one? Yeah. So it's going to be integral to the cube over 3 from 0 to 4. So that's going to be 64 over 3 minus 0. That's approximately what? 64 over 3. 21 point something, right? 21.3 units. So, what do you see in this case? That the midpoint is closer to the real one. This is the real one. This is the real area. The midpoint is close to that.
Pero, ¿para qué te sirve hacerlo de los rectángulos si puedes hacer la integral y que te dé exacto? O sea, cualquier caso se
Okay.
usa.
No, sí. Pregunta típica. Sí, ya sé. Miren, hay dos cosas. Una, lo que les decía hace rato al principio. Antes de que se desarrollara la integral, para encontrar áreas, que hacíamos? Pues encontrar los rectángulos. Entonces, ¿por qué estamos haciendo todo esto? Para que vean precisamente de dónde viene todo el concepto. Aparte que vienen en los exámenes canciones de igual. Pero, la segunda razón, hay más aplicaciones de Riemann sums aparte de la pura integral. Son las mañanas. La que ver nada más es que la parte inicial. Pero sí, o sea, hay más aplicaciones en las que les podemos dar, a lo mejor no una gráfica, sino una tabla de valores. En la que usar Riemann sums es más útil porque una integral, si no tienes la función, no la puedes integrar. Pero con Riemann sums sí puedes tratar de aproximar los valores. Eso sí da muchos problemas de física, por ejemplo, para velocidades que son cambiantes. Entonces, como digamos, la introducción.
¿Por qué la entrada se calcula así? O sea, no tomas en cuenta la luz para nada.
No, you do. But the problem is, for example, in this last rectangle, how do you calculate the height of the rectangle, the white?
O sea, puede estar como 13, ¿no?
Ese es el problema, no puede ser como 13, no es respuesta. Tienes que calcularlo exactamente. ¿Cómo lo calculas exactamente? Pues como ese punto toca la función y la función si la conoces, que es x cuadrada, pues entonces si sabes que este punto, que es 3.6 en x, lo evalúas en la función, te da la altura exacta. Toca. ¿Mandé? Si yo conozco que la base de cada rectángulo es 0.8, ¿cómo lo sé eso? Pues desde el principio. Entonces, estoy diciendo midpoint, pues midpoint es la mitad. Entonces, por ejemplo, si mi área es de 0 a 4, es de 0 más 0.4, que es la mitad, yo tengo el primer valor de x, 0.4, y lo evalúo una función para encontrar la y, que es la altura del rectángulo. Para encontrar el siguiente x, o sea, el del medio, pues es 0.4 más la base para encontrar el siguiente y lo evalúo una función. Y otra vez, más 0.8 me da 2 y lo evalúo una función. Si yo no puedo decir como decir, y, pues es como que es medio, como que es casi 8. No, pues no. O sea, tengo que evaluar una función que le sirva el problema. Sí. Pues para eso me sirve la altura. Por eso estoy haciendo todo esto. Todas estas son alturas. Esta es la base. Es la altura, la altura, la altura, la altura, la altura del primer rectángulo, del segundo, del tercero, del cuarto y del quinto, según la fórmula del área. Pero ¿cómo los encuentro? Metiendo las x dentro de la fórmula, perdón, de la función que me está dando el problema. Si la función sería seno de x, entonces no pondría 4 al cuadrado, pondría seno de 4, seno de 3.2, y así me voy con los demás. ¿Okay? Todos hacemos más ejemplos, esta fue como la introducción. Ok, questions? ¿No? Ya. Another situation from your question. Again, you may think, okay, why do we do the addition? Why is there a reason of that? There is a reason for that. In this case, for example, in GeoShare we have 5 rectangles, right? This is the real one. This is the real one. Imagine that instead of using just 5 rectangles, I use more. I use more. Let's say that I use 12 rectangles. 12 rectangles. According to this applet, the Riemann sum gives you 21.29, which is closer to the real one. If I give you more rectangles, let's say 20, what happens? 21.32. Okay? So, how do we relate this one with the integral? Easy. What's the area of the rectangle? Base 10 pi. According to this, then it will be each area is going to be the base, which is delta x, times what? The height, which is f of xi. What xi? The value for x for each rectangle, right? But to get the whole area on the rectangle, we need to do a sum of what? Of the f of xi delta x from the first rectangle to the last rectangle. N is what? Subintervals. Okay? But what would be the real one? The real area is when the number of subintervals gets close to what? Huh? Huh? No. 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 A ver, reparte la pregunta. Otra vez. Altura, base. Del primero hasta el último que tengo. ¿Sí? Puedo tener 2, 3, 5, 20, por ejemplo. ¿Cuál de todos esos, cuántos necesitaría yo entonces para que realmente encuentre el área real debajo de la curva? ¿Cuántos necesitaría? Pues muchísimos. Infinitos. ¿Sí? Pero no puedo ponerle infinito, ¿verdad? Infinito no es un número. Infinito es un número muy grande, pero es un concepto. Entonces, ¿qué usamos de mate 5? ¿Qué usamos para decir que mi n se aproxima al infinito? Límite. Esto es la suma de Riemann. Es la suma de Riemann. Es la verdadera suma de Riemann. Entonces, ¿qué tiene que ver con la integral? Muy simple. Lo que hicieron matemáticos en el siglo XVIII, XVII fue decir, ok, tengo una significa sumatoria. ¿Qué hacemos? Vamos a hacerla un poquito más bonita, más estilizada. Realmente el símbolo de integración es como una sigma. Una sigma. Es una sigma estilizada, por decir así. Entonces, en lugar de usar límite, sumatoria, bla, 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 esa sumatoria tiene propiedades medio difíciles de entender. Para la primera, si lo hubieran en la universidad ya tendrían más propiedades. Pero esto se resume en una integral. ¿La integral de qué? La integral de a a b de la función que tenga de x. Esta delta x es el de x, cambios muy pequeños. ¿Sí? Esta es la básica de la suma de Riemann. Hay una manera más compleja de la suma de Riemann que también es cuando los intervalos cambian de bases. O sea, que las bases pueden ser grandes chiquitas. Porque en realidad no es obligatorio que todos los rectángulos tengan la misma base. No. Puedo haber rectángulos con las bases cada vez más chiquitas y más chiquitas, y más chiquitas. Pueden cambiar. Y no necesariamente la x debe ser la misma siempre. Entonces, esa es una manera más compleja, pero la forma básica de la suma de Riemann es esta, para poder llegar a esta. Eso es lo que tiene que ver. ¿Ok? ¿Ya has visto mejor?
Sí.
No quiero que se aprendan otra vez límites, no. No quiero que otra vez usen las sumatorias, no. Nomás quieren el concepto básico, sencillo de primaria, de sumar y multiplicar. Nada más. Nada más. ¿Qué tedioso? Pues es tedioso, pero pues es un tema fácil. Si no nos ponemos más integrales más difíciles, entonces ¿cómo fácil? Ok, fine. ¿Questions then? No? Good. Okay, now there's another way that doesn't use rectangles. There's another figure that allows you to approximate even better instead of using rectangles. Those are the trapezoids. So, we're also going to see a trapezoid method. What happened? Yeah. Yeah. Except the same thing. Huh? It's a lot more exact. Not exact, but it's more exact than the rectangle. No, we'll do the graph. Okay, what about the trapezoids? If you observe this figure, I'm using 5 trapezoids, and the area is going to be a lot more exact. Yeah? The problem is that finding the area for the trapezoids is a little hard. Time consuming. Okay? So in this case, this is again delta x, and so on. That's the same thing, doesn't change. But understand that for the rectangle is based on time. Simple. What's the area of a trapezoid? Yeah? That's the area of a trapezoid. Base mayor, más base menor, por altura sobre 2. In these figures, what's the height of the trapezoid? The height of the trapezoid is not the height of this. The height of the trapezoid is the delta x. This is the height now. Why? Do you remember how a trapezoid is? A trapezoid is something like this. In this particular case, like this. This is the height, this is the big base, this is the small base. Okay? But this trapezoid is vertical. So that means that the height of each trapezoid is now the delta x, and each one of the bases is going to be what? Yeah. Yeah, it means that this is 0. So this is 0 based on height over 2. Yes, triangle. But not always it's going to be a triangle. In this case, a triangle because you start at 0. If you were to start at 1 for the area, then it's going to be a trapezoid. you could say that the trapezoid generalizes the triangle in this situation. Okay? So, for example, taking this one, this is the big base and this is the small base. But this is going to be now the big base for the other one, and this is the small base, and so on. Big base, and then this one, and so on. Okay? But the problem here is, since I want to find the bases, I'm going to use f of the value again, like with the rectangles. So I need to find this height, this one, this one, this one, this one, and that one. Okay? So this one is what? F of 0. This one is what? F of 0.8. This one is what? 1.6. This one is what? 2.4. This one is what? 3.2. This one is what? F of 4. So, no. Estoy haciendo el con papel. Okay. Area trapezoid. First trapezoid. The height. The height is what? 0.8 times the big base, which is 0.8 to the square, plus the small base, which is 0 to the square. All of it over 2. Plus, that's the first trapezoid. The second one, 0.8 times the big base, which is 1.6 to the square, plus 0.8 to the square over 2. Because it's x squared. Yes, yes. Plus 0.8, 2.4 to the square. Yeah, that's what's simplified, but before you understand this. 1.6 to the square, all of it over 2, plus 0.8, 3.2 to the square, 2.4 to the square, over 2, plus 0.8, 4 to the square, 3.2 to the square, over 2. Okay? That would be the area of each trapezoid. Yes or no? Yeah. Could I simplify this entire operation? Yes, I can. Because in this case, 0.8 and 2, 0.8 and 2, the same for every trapezoid. We could simplify it by factorizing. So the whole area is going to be 0.4. Multiplying what? Well, this one plus this one plus that one, and so on. But if you notice, for example, except the first value and the last value, all of them repeat 2 times. So you could say, okay, then I have 0 to the square, which is 0, and 4 to the square, which is 16. What about the others? Well, 2 times 0.8 to the square, plus 2 times 1.6 to the square, plus 2 times 2.4 to the square, plus 2 times 3.2 to the square, plus 16. And that's it. But of course, you're not going to see that if you don't know the formulas at the beginning, right? So I'm doing that way so you can see that they are at each other. Okay, we can use this table if you want to. Find them in. As long as you find all of them and then add them. Fine. How much is that?
21.7.
Yeah, it's there. 21.76 units. Which is closer to this one than the other one. That's both, more or less.
Mr. How did you rewrite the formula to what you important?
Factorizing. My factor, 0.4. 1 divided by 2 is 0.4. So and then I factor everything, and then I see that except the first value and the last value, all of them repeat twice. That's why it's 2 times that, 2 times that. And again, y squared, because that's the function, x squared. If the function was the square root of x, it would be square root of the value.
Los que se están repitiendo las cosas multiplicó por
sumamos desde
Yeah.
desde aquí. Y la función de X cuadrado.
Good. Questions? Yeah. Yeah, because the function is the square. I'm sorry, I have to wait the course is done. Sí, yo sé que es tedioso, sé que es empalagoso, que no sé qué hace. Yo sé, pero así está el Okay, questions? No?
Rápido, vamos a verlo eso delta X puede ser distintos.
You only see that if you study something related to math. Not in engineering. Well,
Si estudiamos qué, profe?
algo de math.
Ah, qué bueno.
Tienes que ver propiedades de sumatorias.
Si no están delta X va a dar propiedades que
Okay, let's try summarizing formulas. So we have to do, and then we have to finish, okay? Instead of using from 0, you start with 1. It will be better. So you can see it better. From 1 to 4. 5 rectangles. An example. Going to generalize formulas. Riemann. So remember, we have left endpoints. We have right endpoints. We have midpoints. And we have the trapezoid. Okay. For the left endpoints, remember the left of the rectangle is going to be the height of it. So in this case, remember, is the area left delta x, which is the base of each rectangle factorized, times what? If this is A and this is B, and the areas between A and B, this height is going to be what? F of A. So the first one is going to be F of A plus F of what? A plus delta x plus F of what? A plus 2 delta x all the way F of V minus delta x. Why V minus delta x? Because if you observe, this is V, and the last left endpoint is this one minus delta x to touch the graph. Okay? No need to memorize this. No need to memorize this. Just try to understand that when it's left endpoint, just start with the value of A. And then to get the other value inside the function, you just need to add delta x. And so on and so forth. Okay? I will explain it. B is this one, and the left one is this one, right? So how do I get to this point here? B minus delta x. Okay? Fine. Right endpoints. Right endpoints. For the right endpoints, observe what happens. Now it's going to be for the right endpoints is delta x again, the base, but this time where do I start? It's better to start with the last one. So it's f of b now, plus f of what? What is the next one?
B minus delta x plus f of b minus 2 times delta x, so on until f of a plus delta x, which is the last one. Remember, we're taking the points that touch the graph, not the ones that are outside the graph or below the graph, the ones that touch the graph. For the midpoints, again, delta x times what? Almost done. F of what? What is the first value? A plus delta x over 2 plus f of what? That one plus delta x. It would be a plus 3 times delta x over 2 plus a plus 5 delta x over 2 plus f of b minus delta x over 2. Why 3? Why 5? Because in this case, remember, the first one is this one, but to get the next one, you need to add delta x. Okay? For the trapezoidal method, in this case, using that formula. But if you want to factorize, it will be what? Delta x over what? Over 2. Factorize. Times what? F of a, f of b, and what? 2 times f of a plus delta x plus 2 times f of a plus 2 delta x, and so on until f of b. Is that clear? The last one? It's just what I did in there. Except the first one and the last one. All the other ones are just multiplied by 2. Okay? Or you can just apply the formula every single time, solve it, and then add all of them. It's up to you.
Dice, ¿por qué en la primera tienen el x al final y en la segunda vez?
Because it's this point. So it's b minus the base, which is like this one. Okay. Tomorrow,